What's up, everybody? In this video, we're going to cover USACO's 2019 February contest at the bronze level, problem number 2, the Great Revegetation. A lengthy drought has left Farmer John's end pastures devoid of grass. However, with the rainy season arriving soon, the time has come to revegetate. In Farmer John's shed, he has 4 buckets, each with a different type of grass seed, so 4 types of grass seed. He wishes to sow each pasture with one of these types of seed. Being a dairy farmer, Farmer John wants to make sure each of his cows has a varied diet. Each of M cows has 2 favorite pastures, and he wants to be sure different types of grass are planted in each, so every cow can choose between 2 types of grass. Farmer John knows that no pasture is the favorite of more than 3 cows. Please help Farmer John choose a grass type for each pasture so that the nutritional needs of all cows are satisfied. All right, input format comes from a file, revegetate.in, so you'll have to make a file reader. The first line of input contains N, which is between 2 and 100. That's how many farms there are. And then M, where M is how many cows Farmer John has. So John's got 5 pastures and 6 cows. Let's go ahead and actually draw this one out. So 5 pastures, 1, 2, 3, 4, and 5, and 6 cows. The cows all represent with lines. Each of the next M lines contains 2 integers in the range of 1 to n, describing the pair of pastures that are the 2 favorites for one of Farmer John's cows. So, for example, 4 and 1 are the favorite of one particular cow. So this line then represents a cow, and that cow likes both goes to pasture both 1 and 4. So what that would imply then is that pasture 1 has to have a different type than pasture 4. We've got 4 to 2 and 4 to 3 as well. 4 to 2, 4 to 3. We're guaranteed that no pasture has more than 3 cows, so 4 has the 3 connections, and that's all there is. 2 connects to 5, 1 connects to 2, and 1 connects to 5. So kind of a complicated web, but what we're looking at doing is we're looking at assigning different grass types to every neighbor. So for example, if I had, let's use colors. If I were to assign the blue grass type to pasture 1, then that would mean that 5, 2, and 4 cannot be the blue grass type. So we would have to pick a different grass type for each of those. Let's go ahead and fill those in. So we've got the green grass type for pasture 5, which now means that pasture 2 cannot be blue or green. So let's make pasture 2 yellow. All right, so then pasture 2 is yellow, which means 4 cannot be blue or yellow. Could 4 be green? I think 4 could be green. Yeah, 4 could be green. And then 3 could be blue again. Okay, and we want to try and print the n-digit number that's the smallest. So when we're doing this, this is let me actually read here. So output an n-digit number, each with a range of 1 through 4, describing the grass type to be planted in each field. So we have to number these. I don't have numbers assigned yet. I'm just color coding. The first digit corresponds to the grass type for field 1, the second to field 2, and so forth. If there are multiple valid solutions, print only the n-digit number that is the smallest among them. What they're saying there is just for field 1, you should try to assign grass type 1 instead of grass type 4, for example. So I think I have this all coordinated. So then we're going to go through and assign grass types. So if I say that blue is grass type 1, then I've got blue here, and I've got type 1 here and there. Field 2 then should get the next grass type. So yellow is going to be 2. I have no other yellow. And then green is going to have to be 3 and 3. So if I write these numbers out, field 1 is grass type 1. Field 2 is grass type 2. Field 3 is grass type 1 again. 3 is grass type 1 again. Field 4 is going to be grass type 3. Field 5 is going to be grass type 3. And we can check here and see that that is in fact the solution. Okay, so our logic of kind of color coding and how we're doing this is correct. So what we need to do is we need an efficient way to try and figure out what these numbers are, because obviously we can't really draw a graph and solve the problem. We have to find a way to write code that does it. When writing the code, essentially what you're doing, if I were to rewind back here, like this, like this, like this, like this, like this. Let's say like I were to come to the assumption as a starting point where each of the 4 types is available for each field. So 1, 2, 3, 4, all available. 1, 2, 3, 4, 1, 2, 3, 4. 1, 2, 3, 4, and there's only 4 grass types, so that's all I need. 3, 4. Okay, so we always want to try to assign grass type 1 to field 1. What that means is grass type 1 is no longer available for field 2, or for field 5, or for field 4. We then move to field 2. Field 2, we would like to have grass type 2, which means grass type 2 is no longer available. Field 1, which we've already picked, so it doesn't actually matter, or field 5, or field 4. We then want to go to field 3 and assign the first possible grass type. 1 is in fact available, so we're going to assign 1, which means that we can't have 1 at this field. That's not allowed. We already have that scribbled out. Next up is field 4. I'm going to pick grass type 3. That means grass type 3 would not be available for node 3, or node 2, or node 1. And finally, node 5 can pick the first available grass type, which is 3 again. So essentially what we're doing here is when we assign a grass type to a particular field, we're making that grass type unavailable at all neighboring fields. The question is, how do we then translate this into an algorithm? What I would recommend doing, let me actually clear this and back up here. I'll write the pairs down. 2, 4, 3, 2, 5, 1, 2, 1, 5. Okay, so you've got a maximum of 4 types of grass. Grass type 1, 2, 3, and 4. You also have however many fields you have. In this case, n was 5. So I've got field 1, 2, 3, 4, 5. So what I would recommend doing is build a 2D array where it's full of trues. True, 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 true. What you're going to do then is, as you assign to a particular value, you're going to mark, or as you assign a grass type to a particular field, you're going to mark any neighboring fields in that grass type as false. So for example, I have a connection between 4 and 1. So what that means is that if I were to say that I'm selecting grass type 1 for field 1, that means that in field 4, this has to change to a false because I no longer have that available. Also, 1 connects to 2, so this would have to change to a false. 1 connects to 5, so that has to change to a false. We then have assigned grass type 1 to field 1. We can write that down. So grass type 1. Grass type 2. Type 1 is not available. Or sorry, field 2, grass type 1 is not available. Grass type 2 is available though. So I'm going to put 2 down for my selection for field 2. I then look through all my connections. Let me clean this up here. All right, connections to field 2. Here's a connection from 4 to 2. So for 4 now, grass type 2 is going to become false. Here's a connection from 2 to 5. So it's going to become false here as well. And then 1 to 2, it's going to become false here. And again, it doesn't actually matter since we've already assigned this one, but you might as well change it. All right, so then that's assigned grass type 2 to field 2. Moving along. First available grass type on 3, I iterate through. My first true that I find is here. So that's true. Anything connecting to 3 cannot have grass type 1, so 4 can't have grass type 1. I think that's the only connection, and 4 already has 1 unavailable. Moving on to the next one, we get to field 4. Field 4 is selected grass type 3, because that's the first one that's available. So false, false, true. First one available is grass type 3. Oops, that was 1 for field 3, 3 for field 4. So now I have to go back. Anything that connects to 4 cannot have grass type 3. So 1 can't have 3, 2 can't have 3, and 3 can't have 3. That's fine. We've already assigned those, but we'll go ahead and mark it in anyway. False, false, false. Finally getting to field 5. Field 5, the first one available, if I iterate through, is type 3. And then that makes type 3 available for field 2, which it already didn't have. So at the core, the way you're solving the problem is for each one of the fields, you're looking at each grass type. And the first grass type that's available, you want to take that grass type and then make that grass type unavailable everywhere that connects to that field. Now, one potential limitation, though, is that I've got m of these to iterate through. If I iterate through m of these, then for each of n fields, I've got m iterations to do, which is going to give me O of n m, which is fine, actually. I believe that'll still be well within our time capacity. Let me double check this. With 100 and 150, we could go through each of the 100 fields. And just real quick, time complexity, again, it doesn't come up all that often on bronze. A lot of times in bronze, as long as you have a decent algorithm, you don't have to worry too much. A lot of them can be brute forced, but you do have to pay a little bit of attention to these numbers. Anytime you see a 10 to the fifth, that should be a big red flag that you can't do an n squared algorithm. No n squared. And you may want to look up what that is, but essentially what that is that's saying, if you're not familiar with it, that's saying that you can't compare everything to everything. So if I have like 10 things, if my n was 10, or let's just do like, what is that, 7? If I have 7 things, then an n squared algorithm would mean comparing each thing with each other possible thing, every possible combination. When you have this, the complexity of this grows really, really fast. So we don't want to necessarily compare everything to everything, especially if the number of things we have is 10 to the fifth. Because if I square 10 to the fifth, that happens to hit a billion, and a billion just happens to be the number where modern computers generally can't get it done in less than about a second or two, which also happens to be about where the timeout is for USACO problems. Something that's 10 to the 10th could take upwards of several minutes to solve, and that's not going to work within our time complexity. Usually around 10 to the 9th is about the upper limit of what you want to look at, and less than 10 to the 9th is ideal. So what that means in terms of this problem is if I have each of 100 pastures, 1, 2, 3, 4, all the way down to 100, each one has 4 potential grass types, 1, 2, 3, 4, but then I have 150 potential cows with preferences listed here, then what that means is that if I were to say, okay, I want pasture 1 to be grass type 1, we're going to select that. Then if I have to go through each of these one by one in order to find anything that has grass type 1, in order to know, okay, well, I got to make that unavailable for type 2, and now I got to make it unavailable for type 4. If I have 150 of these to go through, and I have to do that for each one of these, then for each one field that I assign, I have 150 preferences to check, which means the amount of work that it's going to take to complete is going to be 100 times 150. 100 times 150 is 1, 5, 1, 2, 3, 15,000. 15,000 is tiny in terms of programming, so we don't have to worry about optimizing this. So you've got 2 approaches to this. The simplest approach that you can possibly do is you store all of your pairs into some sort of a collection. If you have, Python, you might want to do a list of tuples. For C++, you could do a vector of pairs or just a vector of vectors, and the internal vector could just be a size of 2. Java, honestly, I would just use a vector of vectors, an array list of array lists. That would probably be fine. You could also make a custom pair class if you're so inclined. We don't need to sort them or anything, so needing a custom class isn't really necessary. There's no specific operations. Once we get our list of lists, 4.1, 4.2, 4.3, 2.5, et cetera, then we're going to iterate through. And what we need to do is build this table where we've got basically however many fields we have by 4 of trues. And then as we go through and assign, we'll say, okay, so my I variable will start I equals 1. I'll iterate through these 4 values, checking to see what's the first one available. In this case, it's type 1. And then I have to iterate through all these, finding every one of my pairs that has a 1 either as the first or second value. And whenever I do, whatever the other value is, that one has to be marked as a false for that particular type that I just assigned to that particular grass type. And if I do that, I'm well within time complexity. However, if you're familiar with adjacency lists, an adjacency list will actually let you do this in essentially linear time. And the way adjacency list works is you make a list of lists similar to before, but then for each one of the fields, you have to add to your list every cow that, every other pasture of a cow that likes field 1. So in this case, since field 1 is enjoyed by, or since field 1 connects to field 4, since there is a cow that prefers grass in fields 4 and 1, and since there is a cow that prefers grass in fields 1 and 2, and there's a cow that prefers grass in fields 1 and 5, then what I would do is I would have a vector or a list where my index represents one of the fields, and where all the individual values are all the other fields where that value, whatever's in that field can't be allowed to exist. So here 2, 4, and 5. What that tells me is that field 1 is connected to fields 2, 4, and 5. Connected in that there are 3 cows, and those 3 cows that like field 1, and those 3 cows like fields 2, 4, and 5, which means that 1 cannot connect to 2, or whatever we have in 1, whatever grass type we have in 1 could not be in fields 2, 4, and 5. If we were to do this and build this adjacency list for each of the types, so then 2, is going to connect to 4 and 1, 4 and 1. And again, this is just basically a 2D array. There's nothing fancy happening here. This is at most a size 3, and this is going to be a size n. So field 3 has only 4. Field 4 has 1, 2, and 3, and field 5 has only field 1. If you set it up this way, then actually this becomes a linear time solution instead of a n times n solution. Now, this optimization is not necessary, but if you are feeling like it, this is a good practice for adjacency lists. Adjacency lists are very important in silver problems, and they do come up in, I think they do come up in a couple other bronze problems. But essentially what you're doing is you're building a 2D array. You've got a maximum size in this direction of 3. You've got a maximum size in this direction of n. You can make it either a 2D array with a set size, or you can do, again, an array list of array lists, or a list of lists, or a vector of vectors, or whatever it is that you're working with. And then what you're doing is for each one of these now, as you go through and assign, you're iterating through this. When you get to field 1, you would look here and assign field 1 with grass type 1. And then you can iterate through just these 3 things and set them directly to false. False, false for 4, false for 5. Now, the reason why this is more efficient is because if you have n fields to assign, and every field you assign, you have to run through all of the cow's preferences every single time, then you've got n times n operations, which again is within time complexity. So it's not necessary to use this. This is just a good chance to practice adjacency lists. The reason why this is more efficient, though, is because now as I iterate through, I can immediately know what my neighbors are. And I know that they're 2, 4, and 5, which means now my complexity is going to be n fields times 3, which is essentially O of n. And that means we've switched into a linear algorithm rather than what's essentially not really an n squared algorithm, but this is sort of approaching the idea of a squared algorithm. And this is multiplying by a constant. Generally speaking, if you have variables, you're usually better off multiplying by a constant than multiplying by another variable, especially if m has a chance to grow large. So essentially what you're doing with the adjacency list solution is rather than iterating through all of these every single time, we're only iterating through the neighbors. And again, all you need to do to make this work is if you're working in Java or C++, you just either make an array list of array lists or a vector of vectors, push back however many fields there are, you push back that many vectors to your vector of vectors. And then for each one of them, you'll do your file reader and push back the neighbors of each of these. You also could do this with a map. If you want to do this map as a map, you could have 1 be the key and then the list 2, 4, 5 be the value. But again, that may be a little more advanced than necessary. But again, this is not absolutely necessary in order to solve the problem. The only thing you need to do to solve the problem is focus on building this table here with the trues and falses. And then for each field, find the first thing that's true. You can output it right away, or you can store it in a container if you want to store it and print it out later. You add your field number, which in this case is 1, to your output, and then run through all of m values here. Find anything that connects to field 1, and anything that mentions field 1, you just make the other field into a false in that location. So then 4 can't have grass type 1, false. And whether or not you're using the adjacency list or whether or not you're just brute force iterating through all these, you'll be within your time complexity. One of the things that's kind of important to just pay attention to is the fact that there's only 4 grass types. Means that at most you've got 4 indexes to check here, 1, 2, 3, 4. So just kind of be aware that as you're iterating through, you're looking for your first match, and your first match might be any one of those. But it won't have to go beyond 4 because we're guaranteed that we only have 4 grass types. And the reason why that is because we were guaranteed we only have 3 neighbors. Since each field can only be liked by 3 cows, we're guaranteed we only have 3 connections, which means at most we would need 1 grass type for 1, and then a different grass type potentially for 2, 4, and 5. Although it's not necessary because of the fact we have that limitation of 3. That means that for any given node and 3 neighbors, 1, 2, 3, we at most would need 4 grass types, and that's going to carry through the whole entire set. So that's the algorithm. Build the table of trues and falses. Assign the first available value. And then however you choose to do it, whether it's an adjacency list or whether it's just iterating through, mark that grass type available as unavailable. One other thing to watch out for, I've seen this happen with this happens with Java students on occasion. If you're making your output a string, out equals quotes, and then doing +1, +2 as you assign grass types, you should be aware that every time you do this, this is a linear time expanse, which means that as you're adding out those n fields, you've got an n squared algorithm. If you have, for example, if you have, I don't know, if you have a string that's 99 characters long in Java, and you do plus a single letter, it's got to create a new string and copy all 99 of those characters down to the new string in order to add to the C to the end. The reason why is because strings are immutable in Java. So combining to a string like this is inefficient, which means you're going to be adding in another n squared to your algorithm. Now you're still within time complexity. So in this problem, it doesn't matter. But since we're talking about time complexity, be aware that in Java, you probably do not want to have a string and be adding characters to the end of it one by one. In a situation like that, you probably are better off having an array, assigning the, like an integer array, assigning the integers to the array as you go, and then reprinting the array at the end, or just printing out the variables as you go, just for the sake of complexity. But try to avoid creating a string and then just appending one letter at a time to the end of the string. So that's the problem. Good luck coding it. I'll talk to you on the next one.